Move on to naming simple compounds, and let's start with a binary, right? That means two ionic compounds. So compounds made of two ions. Compounds made of two ions. So when we are naming the positive ion, which is the cation, is usually going to be a metal. So if it's monatomic and metal, it's a cation. Simply use the name of the metal from which it was derived. For example, Al3+, right? Aluminum that's donated 3 electrons to the electron C is just called the aluminum ion. That's it. We just have to say the word ion. That's it. Now, transition metals that form more than one ion are going to require Roman numerals that follow the ion's name. Those are your friend. They tell you what the charge is on that particular ion. So copper +2, when we actually say this name of this ion, it's the copper 2 ion. It's copper 2. Copper 2. Mercury 1 is an exception because it looks like this. Right? So when we say mercury 1, we're actually dealing with kind of like a polyatomic ion because these will actually bond together and act as one unit. So see, it's mercury 2, but because each mercury atom, there are 2 of them, because each mercury atom has a charge of 1 + 1, because there are 2 of them, there's overall +2 charge, right? There are 2 mercury 1s associated with one another. And also on that same note, remember that mercury is a metal that is liquid at room temperature. Yeah, the no space thing between the ion's name and the Roman numeral looks strange, but it is the correct way to do it. So when you're writing like copper 2, so you see how there's no space in here? Right? No space. Right after the name. This system, right, of using the Roman numerals is called the stock system, right? Not as in stock as in like stock car or it comes stock. It's actually named after the person who developed it, Alfred Stock, right? He was a German chemist back in 1916. A common ion is the ammonium ion. So remember, NH3 is called ammonia. When we add one more proton on there, right, because it's just a hydrogen proton, but not the electron, because now we have a charge, it becomes ammonium. Ammonium. Very much in the same way, when we have water and we add a proton, it becomes H3O+. This becomes hydronium. Some exceptions here. No Roman numerals are going to be used with silver, cadmium, and zinc, because even though they are, and they truly are transition metals, right? Here, even though they are truly transition metals, they only form one oxidation state, one valence state, and so they only form one charge. And so because they only form one charge, I don't have to tell you what the charge is using Roman numerals, right? And so if you look back down at this periodic table, see, zinc 2+, aluminum +1, cadmium 2+. They only form one state, so I don't really need to use Roman numerals when using silver, cadmium, or zinc. And we move on to negatively charged ions. Remember, that is an anion. They can be monatomic or polyatomic, right? It is very common for negatively charged anions to be polyatomic. But when they're monatomic, we simply add the suffix ide, ide, to the stem of the non-metal's name. For example, the halogens are called the halides when they ionize. All right, so fluorine becomes fluoride. Things like that. Polyatomic ions. These are very, very common. All right, we'll use them a lot. Oxyanions are simply polyatomics that contain oxygen, right? It's an anion. Most polyatomic ions are anions, but if they have oxygen, they're oxyanions. Makes sense. And so here's one of the patterns that we want to remember, right? These endings, we have hypo, ite, and hyper. So when we say hypo, and then the name of the rest of the polyatomic anion, that means that that polyatomic anion has at least one oxygen. And it has the least number of oxygens, right? So this is an oxyanion, so it has at least one oxygen. But compared to other versions of that polyatomic ion, it has the least oxygens. So my example would be hypochlorite. This should be ite, right? Hypochlorite. And then we have chlorite, right? It doesn't have a prefix, just the suffix. Then it has one more than the hypo. Then we have the ate. Oh, there should be a 3. So this is chlorate. This has one more oxygen than the ite. Right? Remember, hypochlorite, chlorite, chlorate. And then, now, hyper is the opposite of hypo. Hope that makes sense to you. But for some reason, I do not know the answer to this. Typically, we do not actually pronounce the high part. We just say per. But this per stems from hyper. So when I write ClO4 minus, that is the form of this polyatomic ion that has the most oxygens, right? It's hyperoxygen. It has a lot of oxygens. But I don't say the high, so I simply write perchlorate. Right, and so here are those examples written down. I wrote them down anyway. Hypochlorite, chlorite, chlorate, and then the perchlorate. And lastly, when we name these ionic compounds, the positively charged ion's name is given first. Right? So the cation ion goes first. This is the cation ion. Followed by the name of the negative ion. That is the anion. Remember, it has that ending IDE. Right? So an example that you've seen a lot, NaCl. This is sodium. This is chlorine that has ionized, so it is now called chloride. So the name of this substance is sodium chloride.